Good morning. So we will continue with the clutch design aspects. We have been covered these topics, right? And also in last lectures we have discussed about the centrifugal clutches aspect. And today we are going to learn about the dynamic analysis for clutch. Okay. Right. Before going to dynamic analysis, just wanted to give a small, a brief discussion the difference between clutch as well as brake. The brake system is very complicated, right? It's very complicated because it's involved with the various aspects. It's not only about the vehicle dimension, right? The vehicle dimension, the vehicle weight, the speed, right? And also there are three different coefficient of friction are involved. When you talk about three different coefficient of friction, one is your friction lining, that's your friction. The other one is the road surface, road adhesion coefficient of friction. The third one is your rolling friction. All those things are involved. Of course, the application of the brake is to stop the vehicle, right? We stop the vehicle in different condition. The condition would be single stop condition or repeated braking condition, as well as the drag or continued braking condition. So you would have seen that, right? Again, as the size of the vehicle increases, the brake thing also is increased. Okay. When however, if you compare clutch with the brake, clutch is very simple, right? Clutch is very simple, and it won't undergo as similar to brake aspect. The reason is the purpose of a clutch is just to engage and disengage during the start of the vehicle, or changing the speed, or want to stop the vehicle. Okay, these are the three condition you are using the clutch system. Okay, so in that condition, in that case, would you expect heat generation? That is the question, right? You would expect degeneration. Degeneration would be more in brake system, whereas heat generation will be there in the clutch only. This is a rotating. You are assuming that your basic cover plate from the engine side. The other one is the friction lining or friction disc is going to engage. So both are different speed. So both are different speed and try to make a contact. During the contact, the brief time, right? So they will rub each other, right? When they rub each other, the heat is generated. Other than that, it's not much the dynamic aspect. Only is difference would be as you change the speed of the vehicle, right? The rotation of the driven member, that will change, right? So what I want to say that it's it is what I said, during the engagement of the particular gear, the heat generation depends, right? Okay, so we'll go for the dynamic analysis. Here I am going to give straight away equations and the concept. I am not going to derive the equations. This is very basic, simple physics based equations. Okay, so dynamic analysis of clutch. There are T is the engine torque or dynamic torque. That's a source. Then you have a acceleration torque. Right, acceleration torque. TL is the load torque. Ti is the idle torque during the idle time. That's also there will be one torque. Then there is a Ts is the static torque. So we have a 5 different torques: engine torque, acceleration torque, load torque, as well as ideal and static torque. Okay. I'll give explanation about the what is the engine torque, load torque, and so on. T is the is the coming from the engine, or else we can say the dynamic torque. So this is the torque. This torque is the engagement torque is the effective torque. The engagement torque is the effective torque on the shaft while the clutch slipping. Okay, while the clutch slipping in the sense the clutch making contact, right? So that is the effective torque during acceleration or deceleration, right, up to the point of synchronization between the driving and driven members. So that's your engine torque as well as or else a dynamic torque. Okay, the load torque TL okay, which acts on the output shaft or output side, I would say, okay, of the clutch as the result of load. Yeah, that's your load torque. Now the acceleration torque TA the acceleration torque accelerates the given masses right, from n1 speed to n2 speed within the given time. Okay, within the given time. So we have one member is rotating from the engine, so another member rotating, right? I'm talking about the friction plate or disc plate, right? That will be rotating. So when they try to contact each other, right? When they touch each other, again the load depends on the speed of the driven member from the clutch, right? When they're making engagement, so then we'll have acceleration torque. Okay, so normally the acceleration torque, right, equal to TA. What do you expect? We have the torque coming from the engine, right? There is a one torque because of rotative one speed. Similarly, would you expect the clutch also will rotate or will be zero velocity? It depends on the what gear the vehicle is moved. Is it first gear or second gear or third gear? Based on that, there will be a certain velocity. So that's also will have a torque, right? So when the join together, right, then there will be a net torque, right? There will be a net torque which is making as a acceleration torque. Okay, so the TA nothing but your difference between the engine torque and load torque. Normally you can rewrite because everything happening due to the rotation of the masses. So everything we want to convert with respect to the torque aspect. So I is at omega 2 minus omega 1 by t. Okay. So where I is at, I'll explain. T is the acceleration time or slipping time. I is it, okay. Dynamic moment of inertia. So normal inertia, moment of inertia is different. Dynamic in the sense it's rotating, right? It is rotating, yeah. N1 is the speed before acceleration. Whereas N2 speed after acceleration. Okay, so that's fine. So just we wanted to understand about the dynamic of the moment of inertia. Remember, moment of inertia, you know, right? Area moment of inertia, no. So you have the things, okay, to find out the mass thing, right? You mass into radius of gyration. That is what is given. But here, the vehicle is moving in a straight line. The vehicle is moving in straight line. Whereas your rotating component, when you talk about rotating components, we are talking about the clutch things. So that has to be taken care of, right? Because of when rotating, so you will have an inertial effect also. That has to be considered. In fact, remember, in the brake, we derived one term called Km. Right? When the vehicle is moving, right, you have to take the inertial effect of the rotating masses. When I say inertial effect of rotating masses, we have taken care of the not only the wheel, the gearbox and the clutch, right? That's what we have discussed. Remember, similar way, now we are focusing only on the clutch aspect, right? Only clutch aspect. That has to be done. The same thing we are giving you in a different aspect. So assuming that you have a clutch here, this is the just clutch. So there is an input. This is coming from the engine, the shaft. Then it attached to the one gear. Okay, assuming this is your gear. So this is gear 1. Then you have another gear 2. This is your shaft. Okay, just understanding, just schematic purpose only. You have one more gear, and this is shaft. So this is gear 2, and this is gear 3, and this is the input shaft. IS, you can say that. Maybe I will say that. IS, input shaft. I'll say that 1 minute. Yes, input shaft. Okay, and this is your counter shaft. And I will take it as this is the Ki. Okay, the total aspect, the Ki, I will take it as a things. Now, if I want to find out the moment of inertia of the gear 1, right, I1, how do I do that? If I want to find out the moment of inertia of the gear 1, so I have to take the consideration of the shaft, right, the shaft, clutch and gear, all three together, right? All three together, I have to do that. So that would be your polar moment of inertia of the clutch, the moment of a gear plus the shaft. Yeah. So similarly, if I want to do for the gear 2, right? So the polar moment of inertia of counter shaft, that's 1, plus the gear 2 itself, plus the gear 3, right? Z3. So this is what we have to do that. Yeah. So the moment of inertia I2, we need to find out that is the I2 moment of inertia. I2 is reduced to clutch input shaft, right, where that rotating omega 1 speed. Yeah. So if I want to find out I2 reduced with the initial speed of the clutch, it should be what? Proportional to the velocity, right? Yeah. So proportional to the velocity, square of the velocity, in fact, the square. Okay. Speed ratio. Therefore, the total IZ to be accelerated, right, by the clutch on omega 1 speed is given IZ equal to I1 plus I2 reduced with the omega 1 speed, so much kilogram meter square. So if you simplify it, the IZ, what happened, is equivalent to Km, right? I just put this is the M and this is smart. Okay. So now understand that everything, they are rotating different speeds, right? The vehicle is moving in a translation direction, right? I had to accommodate both. So how do I do that here? V square omega square. So I have taken the everything. I have taken care of the your translation as well as rotational things, right? So by this is by converting the effective mass moving in a straight line to the moment of inertia, right? The IS would be equal to Km into M into V square by omega square, where M equal to mass of the body moving in straight line, right? Moving in straight line. V is the velocity of the mass moving in a straight line. Mass moving in straight line. Yes, whereas omega is the angular speed of the shaft. That's the thing, yeah. So now ultimately we need to find out the slipping time. So my question is, so you want to engage, right? You want to engage the clutch by changing the speed. What is the typical duration? Would you expect how much time for slipping aspect? The moment I say slipping aspect, the clutch making release and make a contact, achieve the same relative speed. That's the purpose, right? That's the purpose. So what do you expect the typical slipping time for a clutch? Is it in seconds, a few seconds, or minutes? What do you expect? In seconds only. So in seconds, yeah. So the slipping time Ts, right? The time during the friction right phases of the clutch more relative to another, right, under contact pressure. So that defined as Ts equal to Iz, right, omega 2 minus omega 1 by the torque T minus Tn. In other words, we can I'll simplify that. Depends on the gear engagement, omega I minus omega I plus 1 by Tl. So this is the thing, right? So we got Iz converting into translational rotation. That's what, and we understood about the slipping time, right? So when the slipping time happened, what do you expect? The heat generation will be there, right? The heat generation will be there. Again, the heat generation depends upon the initial velocity and the final velocity, and the I is it. So the heat is generated by an individual or repeated, right, repeated clutch engagement, operation, okay, can be calculated QS equal to half mv square, right? Similar way, I is it omega engine speed. I'm just now making as a even more then the corresponding the change in velocity, the whole square divided by 2 with respect to load factor. This is everything happen per engagement. We are talking about per engagement. Yeah. So the load factor nothing but how much is torque, net torque is transferred during the engagement time. So that is nothing but I is at omega E minus omega I plus 1 whole square by 2 into T minus T. Yeah, this is your load factor. Okay, this is nothing but your load factor. Right. So in typically in clutch, the heat is calculated the number of upward cycle and downward cycles for design aspect. When I say upward cycle and downward cycles, so you will use the clutch for engagement first gear, right? That's one. Second gear, third gear, and fourth gear. So that is entire one thing is upward cycle. Then again downward means so fourth gear, third gear, and second gear, and so on. So that's how the heat is accumulated, right? That's how heat is accumulated. So then the heat, the total heat generated total energy, right, per shifting cycle it's nothing but QS. That's already done. So we want to know that the total heat energy generated per hour. Okay, the TH equal to the QS into number of cycles. So much joule per hour, where N is the number of shift cycles or engagement, both are same, engagement per hour. So this is your thermal equation, QS equal to the how much is it is going to be generated. Okay, just physics, nothing else. It's a simple equations, right? Now we are going to do a problem. Okay, what is that we are going to verify or find out in the clutch dynamic analysis? Okay, we have designed the clutch using uniform wear theory, assuming that you have designed the clutch uniform wear theory. How do you know that is safe? How will you identify, how will you prove the clutch is safe under the design condition? What are the possible way to showcase the clutch is safe? Any idea? One is stress aspect, right? So one is stress aspect. That is purely design about. How about in thermal aspect? You have to make sure that the temperature, whatever the temperature or heat is accumulated during the operation, that should not be exceed from the design value. That's a one way where you can verify the the design aspect for clutch. In fact, we'll do a problem, then you will understand what exactly is happening. Please take down the problem. An automotive vehicle develops a maximum torque 220 Newton meter at 4400 rpm and the corresponding power 138 kilowatt at 7000 rpm. The vehicle weight is given 57.7 kilonewton. The gear ratios are 2.786, 1.614, 1.082 and 0.773 and 0.566. Okay, fine. The final drive ratio is 0.44 1, assuming that the vehicle is traveling in motorway, needs at least 10 up and down shifting cycles of the above nature per hour. A single disc clutch lined with the bronze base centered with the CI cast iron under dry sliding condition is provided. Take the tire diameter is 700 millimeter. Check whether the design is satisfactory or not. If not, please give your comment. Okay. So nothing is given, right? The vehicle maximum torque is given and the maximum power is given and the gear ratio is given, and we need to design a clutch for 10 up and down cycles per hour. No, that's what is given. Okay, but of course you have a tire diameter 700 millimeter. Tire diameter 700 millimeters given. One design input is given. What is that? The friction lining material, right? That is given. You can choose, right? Bronze based sintered cast iron. That is the only one information is given. Other than that, nothing. No other information. Yeah. So how are we going to do this? That's a question. Okay. You can see, so these are the friction lining material, coefficient friction. In fact, this already I have shared in the beginning of the lecture. So these are the 4 possible. So what material is given for our problem? Bronze sintered metal. This is what is given, right? This is given. So this is a dynamic coefficient of friction 0.1 to 0.4. The corresponding pressure is given 1030 to 2070 kilopascal, and the maximum operating temperature between 232 to 677 degrees Celsius. This is given. Okay, so this is the only input we have. So using this input, we are going to design a clutch and also check the validation. Alright, so it's going to be a very elaborate problem. Maybe need 3 lectures to complete this. Okay, so now we know that this is the material, friction material we are going to choose. Yeah. So the maximum pressure is clearly given. Okay. As a design engineer, you have freedom. How much pressure you wanted to have, how much coefficient of friction you can take. So what we could do, we can choose from here we can go for a maximum. The friction is 0.4. So that's one thing is there, and the pressure you can choose either way. Okay, whatever the pressure. So here we are going to choose the maximum, the P allowable pressure 1.7 10 power 3 or 10 power 6 I would say. Yeah. So much Newton per meter square. So these are 2 inputs we have taken. The 2 inputs taken for a bronze sintered metal cast iron friction lining aspect. Okay. Other than that, we don't have any other information, do we? No, right? Okay. So how are we going to proceed? What is the way to proceed? Remember, there is one more relation. If you want to have a maximum torque, what is the relation between the inner diameter and outer diameter? That relationship you can use it. Okay. Are we going to use the uniform pressure theory or uniform wear theory? Uniform wear theory. We can use the uniform wear theory. Okay. So use uniform wear theory. for clutch design, and also with the maximum torque condition. With the maximum torque condition. When you say maximum condition, with d by d, right, supposed to be 0.7 or approximately we take it as a 0.6. So that's a clearly given. Yeah. Right. So using uniform wear theory, the P max, right, P max into D, that should be proportional to the allowable pressure D. I think this is what we derived for uniform wear theory aspect. And we know that D is given from here, D equal to 0.6 times of your T, capital D. So this is your outer dia, and the small d is your inner dia of a clutch things. Okay. Okay. So now we need to find out. Already we know that P max. What is the P max? 1.7, right? Did we choose 1.7 or 1.4? 1.7 only, right? Yeah, 1.7 we have chosen. Yeah. .7 into D, and the P we need to find out. So we will have a, okay. So instead of D we can substitute 0.6 D, and P into D. So this will cancel out. Can you tell me what will be the pressure you would expect here? What is the pressure you would expect? How much? 1.02. Okay. So 1.02 so much Newton per meter square. So this is what you are getting. Yeah. Now we need to find out the total activating load. The total load acting on the clutch P equal to so this is that we know this equation, right? Pi into this is 1.7, right? So this is D by 2. So we substitute here, instead of D we can have a, okay, 0.6 capital small d. Can you tell me what is that your value you are getting? P equal to 1.466. Can you tell me what is the value you are getting? What is the value? With the respect in d square, in terms of d square, small d square. Okay. And we know torque equal to mu P d by d by 4, right? So that's the way we wanted to substitute. And already we know that mu equal to 0.4, and just wanted to know what is the P value. 1.7. Okay, so much d square, right? Yeah, 1.78 d square into this is again you can have a everything in terms of d, you can bring it up. Yeah. This is 1.6, right? This is 1.6 straight away I am bringing by 4, right? But already we know torque equal to how much torque is given from the problem. What is the torque is given in the problem? The torque is given as a 220 Newton meter, right? 220 Newton meter. So just equal to 220 Newton meter. So tell me what will be the inner diameter and outer diameter. That's what you need to do that. Yeah. What is the value you are getting? Sorry, I have taken the different value. That's why I am not able to give the answer. Right. I have taken P max equal to 1.4. For that I am doing the problem. 91 point? Okay, 91.75. Okay, millimeter, and this D would be around 160, something like that, right? So maybe we'll consider D equal to approximately 100 mm. So we'll D equal to approximately 100 mm, and capital D would be 170 mm. I'm just rounding off. Capital D, how much value? 153. Okay, so 153. So much. So I'm just make it to near about 170 because that's what I did here. So I'll choose as a 170 mm and 160 mm. Okay, so do that. Yeah. So this is dimension wise. We are talking about this diameter for the friction lining. Remember please, whatever the diameter is for the friction lining dimensions aspect. Okay. Now what we need to do, we need to do the velocity table similar to gearbox, because that is going to be useful for our heat calculation. The reason why I am saying that, ultimately your I is at equal to, right, Km into M V by omega, right? This is the V omega. So the V is nothing but your vehicle velocity. So that vehicle velocity will change for each gear, right? So in that case we need to have the velocity table also. The velocity table. So the gear, we know that the gear ratio, overall ratio, right? Finally your velocity, vehicle velocity. Right. So this 1, 2, 3, 4, 5. There's 5 speeds. 2.786, 1.614, 1.082, 0.773 and 0.566. These are the gear ratio, right? These are the ratios given. And what is the overall ratio? IO is the overall ratio. That's what you need to know that. Then from there we need to find out the VA. Yeah. So what is the final drive ratio? In the problem given, final drive ratio IF is given what? 4.44. Yeah, 4.44. So you have to multiply that. So when you multiply, so you are expecting 12.370, 7.166, 4.761, 3.432 and 2.513. Okay, of course we are not, this is only the forward speed. There is a reverse speed also, right? There's a reverse speed is 2 in the problem. So for that, this is given you 8.88. Right. Now finally we need to find out the vehicle velocity is nothing but pi d n by 60, right, into the IO, the overall ratio. Right. Question, what is the n value here? Are you going to use the engine speed? Right, that's what we did, right? we are using the engine speed. So what is the engine speed you are going to use it? It's a 4400 rpm or 7000 rpm? Right, question is, will you use which speed you will use? 4400 rpm or will you use the 7000 rpm? That is the question. That's a question. Remember, in the gearbox we have taken the maximum speed, right? We have taken the maximum speed. Okay. So in clutch, what is the speed we are going to use it? Are we going to use the 4004 rpm or 7000 rpm? Okay, I just wanted to give you one more information. This is for the speed at T max, right? This is for maximum torque, whereas this is for maximum power, 7000 rpm. Which one? Which one? Okay. So just think about that. So I will stop now. Right. We will continue in next class. Okay.